Hello. In this video, we are going to derive the molecular vibrations of methane, CH₄, by the CHYM method. We will derive both the stretches and the bends. The first step in applying the CHYM method to determining the normal modes of vibration for a molecule is to sketch the molecule in a particularly appropriate coordinate system. The system we are going to use will be inside of a cube, and we're set up the x-axis to be left and right. The z-axis is vertical, and the positive y-axis is going back into the rear of the cube. We can conveniently inscribe a tetrahedron, such as methane, by putting two of the hydrogen atoms at the opposite corners of the top face of the cube, and the other two hydrogens will be on the opposite corners of the bottom face. And we imagine at the origin, at the very center of the cube, is the carbon atom. Next, we can imagine the stretches as involving a vector going from the central carbon atom to each of the hydrogen atoms. And we can also think of a vector as just the terminal point of the vector going from the origin to that particular point. So we can label this particular hydrogen as R1 as a shorthand for the vector going from carbon to hydrogen, calling that R1. For the second hydrogen atom, we will call that R2. The hydrogen atom at the bottom here we'll call R3. And the last but not least, the final hydrogen atom we'll refer to as R4. For each of these particular points, we want to assign coordinates. And the coordinates have to contain the full symmetry of the molecule involving the TD symmetry, because methane belongs to the point group TD. For the point R1, we notice that to get to this point we go 1 unit in the x direction. We conveniently set up our cube so that the edge length is a value of 2. If that is true, then the coordinates of R1, it is 1 unit in the x direction, so the x coordinate is going to be 1. For the y coordinate is going to be 1. And then we go up 1 unit in the z direction to get to the top face. So that tells us the z coordinate is also 1. So the coordinates of R1 are going to be 1, 1, 1. For our second point, R2, we have to go 1 unit to the left in the x direction, which tells us that the x coordinate is -1. We have to come back towards us 1 unit in the y direction. Going in this direction is positive y. Coming towards us is negative y. So then y coordinate is going to be -1. And to get to this particular point, being it's the top face, the z coordinate of all the points of the top face is z equals 1. So that's the final coordinate. For R3, we can reach R3 by going 1 unit in the x direction, the positive x direction. We have to come back in the y direction 1 unit, so that's -1. And to get to the bottom face of the cube, we have to go -1 unit in the z direction. So its coordinates are going to be 1, -1, and -1. Last but not least, for R4, we have to go 1 unit left, so that's the negative x direction. So our coordinate is -1. We go positive 1 unit in the y direction because we're going to the back, so that's +1. And again, since it's on the bottom face, the z coordinate of all the points on the bottom face of the cube is -1. One thing to notice that is a helpful check on our work is we notice that in each case we have either 0 or 2 negative values. So we always have a positive number of negative coordinates. So if you had chosen the points differently, you might have ended up with a situation where you have an odd number of negative coordinates. And that should carry through all 4 points, R1, R2, R3, and R4. Our next step is to look at the character table for the group TD. And our first irreducible representation is A1. And this has a number of basis functions. It has x squared plus y squared plus z squared, which will certainly work in this case. But if we look all the way to the right, if we have a table with cubic functions, we see that it has a cubic function x, y, z, which is particularly useful in this case. Because we notice that for R1, x times y times z, the value of x is the x coordinate, the value of y is the y coordinate, and the value of z is the z coordinate. So for R1, x, y, z is equal to 1 times 1 times 1, which is simply 1. So that tells us that the coefficient of R1 for this function is going to be 1, so we have R1. Similarly for R2, minus 1 times minus 1 is a positive 1 times plus 1, that is our x, y, z in this case, again gives us a value of plus 1. So our coefficient for R2 is going to be plus 1. So we have R1 plus R2 so far. Next we check for R3. X times y times z is 1 times minus 1 times minus 1. Again, that gives us a coefficient of positive 1, so we have plus R3. For R4, x times y times z is minus 1 times plus 1 times minus 1. Again, we have a value of plus 1 for our coefficient, so that gives us plus R4. So our function to describe the A1 stretching vibration for methane is R1 plus R2 plus R3 plus R4, which means each of these vectors gets bigger at exactly the same time. So all 4 of the carbon-hydrogen bonds get bigger at the same time to get smaller at the same time. Next we have the T2 function, and this is a triply degenerate function which has 3 different basis functions, x, y, and z. So let's first apply the x basis function. So this tells us that the coefficient for the individual vectors to make up the whole vibration is merely we get that by evaluating this function using the coordinates that we have given each of the points. So we notice for R1, its x coordinate is a plus 1, so the coefficient is a plus 1. For R2, the x coordinate is minus 1, so the coefficient is minus 1, so that gives us minus R2. For R3, the x coordinate is plus 1, so our coefficient is plus 1. And similarly for R4, our x coordinate is minus 1, so our coefficient is minus 1. So this particular vibration is R1 minus R2 plus R3 minus R4. And we can interpret a positive value as an increase in the bond length, whereas a negative coefficient is a decrease in the bond length. So as R1 gets bigger, R2 gets smaller, R3 gets bigger, and R4 gets smaller for this particular T2 stretch. Our next basis function is y. So now we plug the value of the y coordinate into this function evaluated, and that will give us the coefficient. For R1, the y coordinate is plus 1, so the coefficient is plus 1. For R2, the y coordinate is minus 1, y, so that gives us minus 1 for the coefficient for R2. For R3, the y coordinate is minus 1, so our coefficient is minus 1. And last but not least, for R4, our y coordinate is plus 1, so our coefficient is plus 1. So this particular T2 stretching vibration is R1 minus R2 minus R3 plus R4. Last but not least, we have the z basis function, and we look at the z coordinate to determine the coefficient of each of the vectors R1 through R4 for this vibration. So for R1, the z coordinate is plus 1, so the coefficient is plus 1. For R2, the z coordinate is plus 1, so the coefficient is plus 1. And similarly, we notice for both R3 and R4, the z coordinate is minus 1, so the coefficients for R3 and R4 are each minus 1. these are triply degenerate. So our last vibration is going to be R1 plus R2 minus R3 minus R4, and this gives us all of the stretching motions so far. Now we are going to derive the bending motions of methane using the Kim method. Again, we're going to use the trick that we can inscribe the tetrahedron conveniently inside of a cube. Here we've drawn 3 separate cubes just so that we don't clutter up one of the cubes trying to show all 6 of the bending motions. So since we have 6 bending motions, we'll represent 2 on each of the 3 cubes for clarity. Recall that one way we can represent a bending motion is as a perpendicular bisector, a bisector of a angle. So in this case, we have an angle go from hydrogen to carbon to hydrogen, and to bisect that angle, we would have a vector that goes through this particular point that is the center of the top face of the cube. Similarly, we can bisect the angle going from hydrogen to hydrogen down here. Again, the vector will go through the center of the bottom face. So let's refer to the top point as B1, because that will describe the first bending motion, and describe the second point as B2. Similarly, we can look at the hydrogen-carbon-hydrogen bond here in the x direction, and we'll call this particular point B3. Again, this vector will go from the origin and go through the center of the rightmost face. For the hydrogen-carbon-hydrogen bond over here, the vector that bisects that angle will go through the center of that face. On the left-hand side, we'll call that point B4. Last but not least, for the y direction, we can have the bisector of the angle from hydrogen, carbon in the center to hydrogen there. This particular vector will go through the center of the back face of the cube, and we'll call that point B5. For the hydrogen, carbon, hydrogen angle in front here, for this front face, the bisector will go through the center of the front face, and we'll describe that point as B6. Now let us list each of the points and the coordinates that go with them. So for B1, we notice it's the center of the top face. So its coordinates are going to be 0, 0, plus 1. For the point B2, it's at the bottom in the center of the face. So its coordinates are going to be 0, 0, and minus 1. We're using the same coordinate system that we had used when we were doing the stretches. Similarly, for B3, it's in the center of the rightmost face, so its x-coordinate is going to be 1, 0, 0. For point B4, it's in the center of the leftmost face, so it has an x-coordinate of minus 1. Last but not least, for the last 2 bends, B5 is at the center of the back face, which gives it a y-coordinate of plus 1, so 0, 1, 0. And for B6, to the center of the front face, that has a y-coordinate of minus 1. And we notice a convenient feature of the bends for methane, if we use this particular coordinate system, is that all the coordinates are either 0, plus 1, or minus 1, and there's only one non-zero coordinate for any one of the particular bends, from B1 to B6. So now let's look at the irreducible representation. And since it's doubly degenerate, there are 2 different basis functions. The first is 2z squared minus x squared minus y squared. So to figure out what these particular bending motions are going to look like, we take the values of x, y, and z from the coordinates, insert them into the basis function, evaluate the basis function, and then this value becomes the coefficient for the particular point. So for the point B1, it has a z value of plus 1. X and y are both 0. So if we evaluate this particular function, we get a value of 2. So 2b1, the coordinate of b1 is a 2 here. Similarly for b2, since z is minus 1, we square minus 1, we get a plus 1. Multiply by 2, we get 2. X and y are both 0, so evaluating this particular function at b2 gives us a coordinate of plus 2b2. Now for the point b3, the x-coordinate is plus 1, x squared is plus 1, we have a minus sign in front, so that gives us a coordinate of minus 1 b3. Similarly for the point b4, x is equal to minus 1, x squared is plus 1, but we have the minus sign in front, so our coordinate is going to be, our coefficient is going to be a minus 1, so that gives us minus b4. For b5, the y-coordinate is 1, and so we evaluate this particular function, and that gives us minus 1 as the coefficient. So we have minus b5. And for b6, since y is equal to minus 1, when it's squared it becomes plus 1, we have the minus 1 in front, so the coefficient is going to be minus 1 b6. So we can interpret this bending motion in that if we have a positive coefficient, that b1 and b2 are getting larger, as b3, b4, b5, and b6 are all getting smaller. But even more than that, the magnitude of the coefficient tells us that for as big as a change in b3, that the increase in b1 and in b2 is twice as large as that. So there is a significance to the coefficients if, when we reduce them to lowest terms, if some are not equal to 1. So that is for the basis function 2z squared minus x squared minus y squared. The second coefficient, the second basis function, is x squared minus y squared. So we're going to evaluate the basis function using the coordinates for the particular point. So one thing to notice right away about post b1 and b2, while it has a non-zero z coordinate, x and y are both 0, so if we evaluate x squared minus y squared for b1 and b2, we get 0. So if a coefficient is 0, we can simply omit writing b1 or b2. For b3, the x coordinate is plus 1, so x squared minus y squared will give us 1. So our coefficient is 1 and we have b3. Similarly for b4, x is equal to minus 1, but when we square it we get a plus 1. So the coefficient for b4 is going to be a positive 1. For b5, the y coordinate is plus 1. We square it, but then we have minus y squared. So our coefficient is going to be minus 1. So we have minus b5. Similarly for b6, y is equal to minus 1. When we square it and then multiply by minus 1, we get a coefficient of minus 1 for b6. So for this particular bending motion, b3 and b4 get bigger, whereas b5 and b6 get smaller. So this is the doubly degenerate irreducible representation for the bends. We also have the T2 bending motions here. As we recall, the first of the basis functions for T2 is x. So we look at the x coordinate for each of the particular points from b1 to b6, and that gives us the coefficient for that particular point, or vector if you want to think of it that way. So for b1, the x coordinate is 0, b2 is 0, so the coefficients for b1 or b2 will be 0, so we omit them. For b3, the x coordinate is plus 1, so we have plus 1 b3. And for b4, the x coordinate is going to be minus 1, so the coefficient is minus 1. So this motion is simply going to be b3 minus b4. We notice for b5 and b6 that the x coordinate is 0, so these will not apply. Now for the basis function y, we can kind of speed this up a bit since we notice that for b1 through b4, the y coordinates are all equal to 0, so the y coefficients would be 0. So the only non-zero y values we have are for b5 and b6. b5 is plus 1, and b6 is minus 1. So we can quickly derive these particular bending motions. And last but not least, we have the z basis function. And we notice that the only points that have a non-zero z coordinate are b1 and b2. b1 is plus 1, and b2 is minus 1. So these are the last three of the bending motions for methane. Now for the final points. We know that since methane is a nonlinear molecule, it's going to have 3n-6 vibrations, where n is the number of atoms in the molecule, which for methane is 5. So that gives us 15 minus 6, which is equal to 9 vibrations. And we have derived so far 4 stretching motions and 5 bending motions, which gives us a total of 9. Now you may be curious as to, what about, is there an A1 bend? And we notice that if we were to evaluate the basis functions for A1, particularly the x squared plus y squared plus z squared, we would actually seem to derive a bending motion B1 plus B2 plus B3 plus B4 plus B5 plus B6. But on other grounds, we can reject such a bending motion. That would be that all 6 of these bond angles increase at the same time. But that is not possible because already they take up all space. So there's no way for them all simultaneously to get larger at the same time. So by reason of geometry, we can reject such a bending motion. We can also realize that by the process of elimination, by evaluating all the other particular examples of the basis functions, if they're evaluated to not be identically zero, then a particular stretch or bending motion is known to exist, and we have figured out all 9 of those bending motions. I thank you very much for your attention. Have a good one.